Hold on a second, everybody. I gotta get the projector in the room working. All right. Projector. Also thought we would be on Zoom. Okay. So today we're finishing up with our forces for pulmonary ventilation, hopefully. Next time we'll get into factors, but we'll see. Okay, so we're going to start out with a couple of example questions using pressures, because I know those are kind of confusing as we started to introduce them. So I want us to make sure we get a bunch of practice so that hopefully by the end of the unit, these pressures are easy peasy. Take a look. Given these pressures, you just want to figure out whether air is going to move into the lungs, inspiration, or whether it's going to be moving out of the lungs, expiration. Okay. So hopefully we're keying in on our most important number here because we're looking at relative pressures. We gave the atmospheric pressure is 0, telling us the relative pressures. You can see these are all sort of one-digit numbers, also tells us their relative pressures. Because we have a negative number for the alveolar pressure, it's less than the pressure of the atmosphere. So we're going to move into the alveoli towards that negative pressure. So we're moving from high to low, just down the pressure gradient. So that's what this tells us. We're looking at the pressure outside. So that's the atmosphere versus inside the lung, the alveolar. And to answer this type of question, we don't need to worry about the pressure of this intrapleural space. Right? So, change the number here. So hopefully for this, we're still looking at that same factor. But what do we notice about our alveolar pressure now? There are 3 of you in the room. You want to tell me what it is? Read it out. 0. It's 0, right? So there's no pressure gradient here. Since there's no pressure gradient, this actually means we won't have movement at all. So when they're equal, nothing's moving in or out. And then one more change. As you might expect, gave you an in, gave you a no movement. So this is the kind of pressure we see if we're moving out. So now our alveolar pressure is higher than the atmosphere. So now we have high pressure in the alveoli. We have low pressure outside. So we have air moving out. to decide inspiration versus expiration, that's all we need to look at. We do have one other measurement we may be interested in, and this would be more important if you're thinking about interventions, if you're putting someone on a respirator, you might be interested in this. So to calculate our transpulmonary pressure, this is asking us what the difference across the lung is. So not comparing to the external environment, but just comparing to within this pleural sac. So all we do for this is we subtract from our alveolar pressure, we subtract the intrapleural pressure. So if we do that, 1 minus -4. We get a transpulmonary pressure of 5. So this is just telling us the difference between those two numbers. All of these pressures that I've given you in these examples are normal lung pressures. We're going to see pressures like these throughout normal respiration. So this is like a typical range. If you see values outside of these ranges, something different and weird is going on. Okay, so when we left off, we were talking about Boyle's law and the ideal gas law. Really what we need to know from this is just that there's a relationship between pressure and volume, and they're the inverse of each other. So we have this whole equation, EV equals nRT. R, unfortunately here, is not resistance. It's just a constant. So we're gonna basically ignore almost all of these numbers. The only part we're interested in really is the P and the V. So if we were to reshape this equation, we could say P equals nRT divided by V. And since we don't care about any of these for our purposes, this just shows us that if volume increases, given no changes in anything else, pressure is going to go down. So it's just like that relationship between flow and resistance. We have this relationship between pressure and volume. And we can also look at that conceptually if we don't want to look at it mathematically. So when we say volume, and throughout this chapter, this is kind of important to realize, when we say volume, we're not talking about the amount of stuff. That would be the N, so this would be like moles of the gas. When we say volume, we're talking about the physical size of the container. So as we talk through respiration, we're going to be talking about the volume of an alveolus, the volume of the alveoli. So what we're saying there is not how much air is in them, but we're saying physically how much space do the alveoli take up? Physically, how big are those containers? So we can see that if we have a larger container, but the same number of molecules, the same amount of gas inside, we're going to have a lower pressure, basically because these molecules can spread out better. So they're not exerting as much force. They're not bouncing against the walls conceptually. If we make that volume of the container, if we make it smaller, we now have more pressure, right? We have the same amount of stuff inside, but the pressure is higher because we've packed everything tighter together. So that's really all we have to get out of the ideal gas law for our purposes for understanding respiration. Pressure and volume are inverse. And we thought about that as we thought about the heart. So hopefully that's not too revolutionary a concept for us. We didn't look at this equation. We weren't thinking about gas specifically, but it's the same thing, really. So as we think about breathing, we know that whether we breathe in or breathe out, we're comparing that pressure in the alveoli versus the pressure in the environment. But we know we have a cycle of breathing, so we know that that intraalveolar pressure is going to be changing, right? because we're going to be changing whether it's higher or lower than the environment in order to breathe cyclically, have our normal, our normal breathing, right? So the direct factors that are going to make a difference there are the amount of air in the alveoli, so actually physically the amount of gas, and also the volume of the alveoli. So how big that alveolus is, like what its area would be. Sorry. Not area because it's volume, but you get the idea. How big across the alveolus is. So we're going to see the size of the alveoli change as they get pulled on by the forces in the thorax. And we're also going to see the amount of air in the alveoli change as we breathe in and bring more air in, and as we breathe out and squeeze air out. So both of those factors, the quantity of air and the volume, are going to change, and they're going to cause differences in pressure. So when your lungs expand, when they get bigger, the alveoli get bigger. So as the lungs expand, alveolar volume increases. So what we're saying, right? We have one lung, two lung, really bad lungs. Okay. But do a slightly better job this time. Okay. As the lungs get bigger, the alveoli get bigger. All right, so as we stretch the lungs out, we also stretch out the alveoli. Before we have any air move into those alveoli, this means that the pressure in the alveolus is going to drop. So like we had our small alveolus and then we have our big alveolus. If we have no change in the amount of gas, all right, so we have two little gas molecules. Now we have two little gas molecules. There is lower pressure in the larger alveolus. So this would be low alveolar pressure versus higher alveolar pressure. And that's just because of that pressure volume relationship. All right, so we have the pressure roughly equal to some constant over the volume, right? So we've increased the volume, that's the size of the alveolus. So because we increase our divisor, and these are inverse relationships, this means that we're decreasing the pressure. As we decrease the pressure, our atmosphere is always at zero because that's always what we're comparing to. So as we decrease alveolar pressure, it gets more negative, right? So if we start out, we're not breathing in, our pressure in the alveoli is zero. So our pressure difference will be zero for the atmospheric pressure. Minus zero for the alveolar pressure, giving us no pressure difference. But as we start to drop our alveolar pressure down, right, say 0, minus, -1, now we have a pressure difference, right? So now that we have a pressure difference, we're going to be able to have flow, because we know that flow is a difference in pressure divided by some resistance. So if we don't have any pressure difference, we're dividing at 0, nothing's going to happen. But once we have a positive number here, we're going to have a flow. You don't have to worry about doing that math specifically if it doesn't help you. If it helps you more to just think about it conceptually, that's fine. But if you want to do the math, if you find that useful, that's really what we're talking about in terms of relating these properties. So as we decrease alveolar pressure, because the lungs are expanding, the alveolar volume is expanding, meaning we're going to have a greater pressure difference compared to the environment. That's what's happening during inspiration. So breathing in. And we will see these words officially on the slides in a bit, but that's happening in order to bring air into the lungs. But to drive air out of the lungs, we're going to have the opposite thing happen. So this is going to be called expiration. So after you breathe in a big breath, your pressure in the alveoli decreases, but you bring in more gas molecules until you're back at zero compared to the environment. And then when you breathe out, what first happens is that your lungs, and also your thorax, are going to recoil. So they're going to be bouncing back. They're going to be contracting and getting smaller again. So we have the opposite thing going on with the alveoli, right? So now we're starting with a large alveolus. And as the lungs get smaller because of the recoil, now we're going to have a smaller alveolus. So we're going to be compressing that gas more because the alveolar volume got smaller. So now we have a higher pressure in the alveoli, and this is going to drive air out of the lungs. So we'll still have a pressure difference, but it will be in the opposite direction, pushing the air out. We're going to have a couple of figures like this, which I actually find helpful for relating all of our different factors here. So what this is showing us up at the top is first whether we're breathing in, inspiration, or whether we're breathing out, expiration. And then it's giving us our alveolar pressure. So the pressure in a single alveolus. And also how much air is in the lungs. So that's our breath volume. And it's relating that to these pictures so that we can kind of understand what's going on with the intraalveolar pressure. So we see at the beginning here, we have 1, 2, 3, 4, 5, 6 little dots in here representing our air molecules. We're saying at the beginning here, our pressure is equal to atmospheric pressure, so nothing's happening. In order to breathe in, we need to decrease that intraalveolar pressure. And as we do that, our alveoli are expanding, right? That's how we are decreasing the pressure. We're making them bigger. And this is dropping that pressure down, pulling air towards it. As this pressure is dropping, some air is coming in. So this is why we start to see the breath volume going up. And we'll see at a certain point, there's an inflection point here. So we are now at the lowest alveolar pressure here at this point. And the reason that that intraalveolar pressure goes up during the second half is because these air molecules are physically moving in and the alveolus has expanded as much as it can. So that's what's going on with this upward slope. Now you are still breathing here until we get back to zero, even though the intraalveolar pressure is going up. So long as it's below zero, it doesn't matter. The whole time it's below zero, you're breathing in, whether this line is decreasing or increasing. So now we can see this next time we're at zero, we have a larger alveolus with more gas in it. So if we were to compare these two pictures, this one and this one, they have the same pressure, but the alveolus is at a different volume. They have different amounts of gas inside. That's the difference here. but they'd be at the same pressure, which is 0. The next, for expiration, now we're going to want to be pushing air out. So the way we're doing that is we're shrinking the alveolus. So as the lungs recoil, the rib cage moves in, pushing that alveolus smaller. This gets us higher pressures in the alveoli, which forces the air out. So conceptually, it's just like when we had the ventricles contract, squeezing blood out of the heart. It just may feel a little different because we're talking about air, and that doesn't feel quite the same as a fluid, but from a physics perspective, it works exactly the same. We're squeezing this alveolus smaller, so air shoots out. Then we come back to 0 again because we've removed some air. So eventually we reach a point where we're at equilibrium with the environment again because we have a lesser number of air molecules inside. So questions about this graph or this sort of process of a cycle of respiration. We will keep touching back here as we talk about different forces, but this is really the basis for everything that we're talking about in this unit. It's really important to understand what's going on with these pressures, these volumes, and these cycles of breathing, because if you don't understand these when we start to talk about different lung volumes and different pathological conditions, it's not really going to make sense. I'm all on it. We'll keep practicing. If you come up with questions, please let me know, and we can talk about this in a different way. Or I'll try to find a different way to talk about it. Okay. So, in order to change these alveoli, to change their size, we've said that they're changing size as the lungs change size. Right? The volume is changing because the volume of the lung itself is changing. Now, the reason for that in inspiration is mainly because of the diaphragm, but also these muscles called your external intercostals. I'm going to draw a rib cage on here. Right, so here's our rib cage. Oops. Very bad at drawing rib cages and everything else. Sternum, rib cage. Okay. So intercostal muscles are where they say they are. Costal means ribs, so intercostal is just connecting ribs to each other. So we have external ones and internal ones, outside versus inside. So that explains those. And the external intercostals specifically basically kind of pick up the ribs and pull them up and out. So this expands the rib cage to the sides. But the diaphragm is really the bigger deal, the more important thing. So when the diaphragm contracts, actually, let's talk about the diaphragm first. I'm getting ahead of myself. So the diaphragm is a muscle that forms like the base of your thorax. So we find our diaphragm here separating our thorax from the abdomen. When it is contracted, it's pulled tight, right? That's what contraction does. It pulls something tight. So when it's contracted, it's going to look flat like this. When the diaphragm relaxes, it'll bow up like that. So its contracted state is down. Its relaxed state is up. So when it contracts, it's basically pulling everything in the thorax down. It's opening up the thorax, making more space in the thorax because it's like squishing that lump that existed before. So when the diaphragm contracts, the thorax gets bigger. This means that when we talk about expiration, we do have some muscles listed here, But usually in passive expiration, so if you're just easy breathing, you don't really use any muscles at all. What happens is you go from this relaxed state, this contracted state of the diaphragm, and you relax. So instead of being this flat line at the bottom, that's our contracted state. Our relaxed state is going to bow up like this. Right? You can see that this muscle is now longer. That's how we can tell it's relaxed, right? It got longer when it relaxed. And there's now just less room for the thorax because the contents of our abdominal cavity are kind of poking up into the thorax. So there's less room there. And this is a passive process, just relaxing the diaphragm mostly. It's going to be aided by the recoil of the lungs. So the fact that they want to bounce back. The ribs are also going to want to bounce back. We are going to see some muscles involved if we want to really rapidly, forcefully expire, breathe out, right? Like there's a difference between just like silent breathing out and you can even feel it, right? Everybody just like breathe out real hard right now. No need to do it because I can't hear you, but that's okay. You can feel your abs contract when you do that. You can feel your abdominal muscles contract because what they're doing is they're pushing your abdominal organs tighter together, which forces them up harder, kind of under the diaphragm and pushes into the thorax a bit. So the abdominal muscles and also the internal intercostals, which also run between the ribs, you can use them to breathe out, to expire, but only when you're really trying, only when you're noticeably breathing out forced breaths. So here we see pictures of those. So the diaphragm there, it's in purple. Right. So diaphragm in purple. The diaphragm is here. So we can see here it's in its relaxed state, which means this is a picture taken during expiration, right? And we can see the location of our intercostal muscles. We have our external ones, we have our internal ones, and we would also include our abdominal muscles if we're thinking about everything that can affect breathing. So here you also see the difference in cross-section of the chest wall. Right, so inspiration, big chest, big alveoli, low alveolar pressure, as those ribs have moved up and out, versus small rib cage during expiration, putting pressure. And then making a big difference is the contraction of the diaphragm. So here we have an overall larger space for our lungs than if we look at this image here. So the diaphragm is moving down, giving us more space in this superior inferior direction. So if we're thinking about a cycle of breath, we start with neural stimulation. So we start with nerves. So a specific nerve called your phrenic nerve runs down from your neck to your diaphragm. When we send an action potential down that nerve, it tells the diaphragm to contract. So as the diaphragm contracts, moves down, opening up that thorax from the lower portion, right? So it's expanding into where your abdominal cavity was before. The external intercostals also contract, pivoting the ribs up and out. So we've expanded in all directions in response to these nerves sending their action potential. This means our thoracic cavity volume has increased, it got bigger. And this has an effect on some of our pressures, specifically our intrapleural pressure. This dropped our intrapleural pressure down which we can think of as kind of the pull out on the lungs. So as that rib cage expanded, it exerted a pull on the pleura and therefore on the lung. So our transpulmonary pressure would have gotten higher because that's the difference between the alveoli and the intrapleural pressure, which has been affected by this change in the rib cage. So our alveoli got larger, so we had volume change of the alveoli, which means we also affected the pressure. Drops down because volume goes up, pressure goes down, they're inverse. Now that we have a low alveolar pressure, the air flows into the alveoli because flow is controlled by pressure gradients. So we're going to go through a chart of this. So we're starting out with our motor neurons. We can see that our initial stimulus, you're sending action potentials to the muscles of inspiration, telling them to contract. So our diaphragm and external intercostal muscles contract now. So as they contract, our thorax expands. Our chest wall is expanding up and out. Our diaphragm is expanding us below the thorax, basically. So as it flattens out, it pulls down, gives us more space in that downward direction. This pulls on the intrapleural space. So this says the fluid because when we're thinking about that intrapleural space, right, a lung here, and another lung here. Our pleural space is this pleural sac around the lung. Right. So it's folded back. And we have some fluid in here. Right. So as the chest wall is expanding out, it's pulling on that fluid, which means we're also going to pull on the lung. Okay. So because we're pulling on the fluid, this means the pressure here is dropping. So our intrapleural pressure is the pressure in this space, in this fluid-filled pleural sac. Increasing our transpulmonary pressure. So this is increasing the difference across the wall of the lung, so between the alveoli here and that intrapleural space. Which means as we're pulling on those alveoli, they're going to get bigger. As they get bigger, this means the pressure goes down because they're greater in volume, but we haven't had a change in their contents yet. This is telling us we're increasing the difference in pressure. We don't have to calculate this because when we give relative pressures, we know this because we know a negative alveolar pressure tells us that there's a pressure difference. This has the air flowing into the alveoli to fill up that space that we've created fundamentally. This is considered a negative feedback loop because as we have more air flow into the alveoli, our pressure in the alveoli goes back up. Eventually it'll go back to zero, which means we will have completely filled up that increase in volume in the alveolus, which means we're no longer going to have airflow in. That's going to be time to expire. We're going to allow everything to recoil. We're going to allow everything to bounce back, which will make the alveoli smaller, increase their pressure and push the air out. So here's the same image from before, more or less, except we can see we've added on here what's going on with the transpulmonary pressure. Or sorry, well, we haven't added what's going on with the transpulmonary pressure, but we've done that because we're also looking at the pressure in the intrapleural space. So we can see that during inspiration, like the whole time, it's dropping. Our intrapleural pressure is dropping, and our transpulmonary pressure, the difference between the alveoli and that pressure in the pleural sac, is increasing. If we compare this to this, and it got bigger. We think of this pressure as the pull on the lungs, essentially. And as we expire, that pull on the lungs is decreasing because the pressure in the intrapleural space is going up. Basically meaning we no longer have this pull on the alveoli from outside, and they're therefore able to recoil back to their original size. So expiration, breathing out, normally passive because all we have to do is let the diaphragm relax, let those external intercostals relax, and then we're done. We've made the thorax smaller. We didn't actually have to contract anything to make the thorax smaller. But if we want them to get really small really fast, if we want to forcefully breathe out, or if we want to breathe more air out than usual, we can contract the expiratory muscles, so the internal intercostals and the abdominal muscles, in order to breathe out faster and more volume, basically. So usually, expiration, passive. You don't actually need to send any signal to breathe out if you just want to breathe out easily and normally. That brings us into factors that affect these processes. So ventilation is inspiration plus expiration, so that physical moving air in and out. And now we're going to talk about our old friends, compliance and resistance. So thus far, we've really just been focusing on pressures, right? So we know why that is, right? We have flow, difference in pressure divided by resistance. So all we've been talking about so far is pressure differences and whether that directs flow in or out of the lungs. But now we're going to think about resistance, so how we can control how fast that flow is going, for example. We're also going to be thinking about compliance, which also has to do with the relationship between pressure and volume. But basically, it's like how much pressure do you have to exert in order to have a change in volume. So lung compliance is basically going to be referring to like how forcefully do you have to breathe? How hard do you have to contract those muscles to get the alveoli to expand as much as you want them to? So given we've already talked about resistance in the circulatory system and the cardiovascular system, we can probably predict why we would think of a conducting zone as having low resistance. Our radii are getting smaller as we move towards the respiratory zone, but hopefully we remember that we have lots of branching. So despite the fact that any individual tube's radius would be small, because there are so many of them, when we think about the resistance of the lung collectively, we don't have all that much resistance. All right. So compliance, we can think of as how easy it is to stretch the lungs. If you have greater lung compliance, This makes it easier to breathe. Now, looking at the equation in this way is not very intuitive to me, so I am going to reshape it. If it makes sense in this shape to you, you can leave it alone. I just find multiplication easier. So I'm going to reshape this to say that compliance times our difference in pressure. I'm not going to write out that whole equation. Compliance times a difference in pressure creates a difference in volume. So what this is saying is that if we have a small compliance, we need a relatively large difference in pressure to create a large change in volume. But if we have a high compliance, we only need a small difference in pressure to create that same difference in volume. So we want our lungs to be compliant. We want them to be highly compliant. We want large lung compliance because we don't want to have to work that hard to breathe, right? We have to create this pressure difference. We have to create that difference in pressure between the alveoli and the interpleural space in order to control the difference in pressure with the environment. We have to create it with our muscles. We have to create it by changing the size of our thorax. It is convenient for us to be able to do this easily without thinking about it. And you can think about it if you've ever struggled to breathe, right? You had to consciously move your muscles, right? You know you don't want to do that. You know you don't want to have to expend much effort in order to make your lungs expand. So there are some factors that affect how compliant the lungs are. Like we saw in the circulatory system, there's a trade-off between elasticity and compliance. So in our cardiovascular system, we said that our arteries were a pressure reservoir. They were highly elastic, but they had low compliance, versus our veins, not very bouncy, not very elastic, but they are highly compliant, meaning they could collect a lot of blood. They could act as a volume reservoir. So the same thing happens in our lungs. If they're more elastic, they're less compliant. If they're less elastic, they're more compliant. There's this trade-off. So we want to think about our lungs as being a little bit more like the veins in terms of their compliance. Another thing that affects compliance that we didn't think about before is the surface tension. So the alveoli do have fluid inside them, right? We've humidified and warmed our air in the conducting zone. We want there to be humidity in the air. But this means that we have a thin layer basically of water in the alveoli. And I think you've probably done those experiments where you put like water droplets on a penny so that you can see how it creates like a little dome because water has surface tension. But this does present a problem for our lungs, for our alveoli. That surface tension creates a force from within the alveoli, pulling them inward, trying to keep them small, trying to collapse them. Now, this means that we have greater tension, kind of pulling them in, stopping us from expanding, which does make the lungs less compliant, right? It makes it harder to increase their volume. We have to have a greater difference in pressure in order to pull that layer of water apart in order to fight against that surface tension. Fortunately, we have this substance surfactant. So surfactant is secreted from the type 2 alveolar cells. So not the ones that were creating that barrier for diffusion for gas, but the other ones that are interspersed throughout. And surfactant is basically like detergent. So it's going to squeeze in between the water molecules and stop them from interacting with each other to create surface tension. So it's just going to break up that collection of molecules so that they don't interact as much. This means that if we have more surfactant, if we have more of this substance that breaks up the surface tension of those water molecules, it makes our lungs more compliant and it makes it easier to breathe. We'll look at just one quick picture. This is from a section in your book, one of those sort of like purple boxes. Frankly, it's addressing a problem that had not occurred to me when I read the rest of the chapter, so it may not have occurred to you either, in which case I wouldn't worry too much about it. But basically, this is helpful for kind of looking at what's going on with the water molecules. So think of these arrows as being water molecules pushing inside towards the air here. So it is the case that in a small alveolus, and our alveoli are different sizes, they're not all like one uniform size, you have small ones and big ones. So it is the case that in a small alveolus, those water molecules are kind of close to each other, so they're pulling in pretty hard on this air. So without surfactant, this would basically force the air in those small alveoli out and into the larger ones, where we'd basically have lower pressure, right? So they would move from one part of the lung to the other part of the lung. Fortunately, this is not what happens, and the reason for that is surfactant. Let's see if it clicks on. Yeah, okay. So here we see the surfactant molecules now getting in between our water. So because the surfactant is here to block the interaction of the water molecules, they don't pull towards each other quite so much, which means that we basically don't have this huge increase in pressure in the small alveoli because we manufacture enough surfactant to combat it. And it is also true that the smaller alveoli have more surfactant in order to kind of compensate for their small size. So this equation theoretically explains this relationship. So what this is telling you is that the tension, twice the tension divided by the radius in an alveolus is the pressure. I'm not going to ask you to do these calculations. All you need to understand here basically is that those water molecules do exert pressure on the air in air, but we can break it up with surfactant, making it easier to breathe, making it so that we have enough compliance so that we don't have to pull too hard on those alveoli to expand them. So we'll pick up here next time and we'll be talking about resistance. And next time I see you will be Friday. So enjoy your hopefully maybe snow day tomorrow. I think we all got an email about at least school being closed. I don't know what your Tuesday professors are doing with your classes specifically. And you'll have Wednesday to volunteer. I'll see you Friday.